Thank you, Ross. I appreciate that introduction. Good morning, good afternoon, or good evening, wherever you are. Welcome. This is our fifth module of Power Seminar series that you guys have probably attended. And in this segment, we're going to talk about how to perform a power quality survey. We're sort of going to take all the things that we learned in the previous segments and kind of put them together as far as performing a survey. I know, many years ago when I first introduced the power quality and went all, the aspects of power quality, you have all this information now, and the first thing you want to do is you want to go out and basically perform a survey and collect data. So we're going to, as soon as I get this thing to advance here, we're going to talk about some of those things. So we'll introduce our staff. I'm joined by Ross Segno. He was the host earlier. I'm also joined by Ken DeMario. Ken DeMario is in our technical support group. You guys have probably spoken to him at one time or another. We will have a question and answer segment at the end. So just save your chats. Just go ahead and chat up when you have these questions, and then at the end of our segment, we'll address each question. Fine, and this is the final segment of our power quality seminar, and I want to thank you in advance for your participation. Please, any suggestions for future meetings, please let us know. We plan to resume this after a brief hiatus of about a couple of weeks, and so your suggestions is very important as far as what our additional future webinars will be. So there's systematic steps as far as conduct a power quality seminar or a power seminar. I'm going to say power from now on because it could be power quality, it could be energy demand, depending on what your application is. So I'm not just going to say power quality from now on. But there are systematic steps that you would take in performing a seminar. So a lot of preparation work even before you go out to the site, things of that nature. We'll talk about all those. And as Ross mentioned earlier, we'll be recording today's presentation. So a little bit about Dranis Technologies. You guys have heard of Dranis. We've been around since the early 1960s. Where we're located geographically, here's the map here. Here's New York City. We're roughly 45 minutes, half hour, 45-minute drive from New York City. A better geographic reference is New York City and Philadelphia are sort of diagonally distant from each other. So if you take that diagonal line and put us right in the middle, that's where we're located. So this is our portfolio and service. As you know, you guys that have Dranis instrumentation, we're known for our three-phase portable power quality and demand instruments, also permanently installed power instruments as well. Our analysis software from our sister company Electrotech Concepts, it's PQView. We're also a U.S. master distributor for Gauss and Metrowatt products, such as precision multimeters and testers, electrical safety installation, and other testers. So we're a master distributor for Gauss. And as always, we have free technical support. We also provide on-site training when conditions warrant it. Most of these days during the pandemic, it's been virtually remote, and that has worked out fairly well. We've actually have gotten smarter in terms of remote training and remote product commissioning. So, so there was some positives out of this pandemic that we're presently in. And then of course our website, which is chock full of information. I tell users to check our website periodically for new information such as case studies, new product info. It's a wealth of information there at dranis.com. Visually, here's our product offering. We talked about the services that we have, but our product offering from permanently installed, we've expanded that area to portable instrumentation, that what Dranis was really first put on the map. And then, of course, our newer product was the DRAN Expert, and I would suggest that you go to our website when you have time to view details on the new DRAN Expert. We're really excited about that. The feedback from potential users they've been excited as well. And then, of course, our software, PQView, PQView DE, system software, DRANView, as well as software that's used for portables. And then again, since we are a master distributor for Gaussian, you see the line of safety, installation, and other testers. So let's talk about how to perform a power survey. And there's different types of surveys. They can be separate, they can be combined, depending on what your application is. And most of the time we hear power quality, because there's a power quality event, or you have suffered a power quality event that's actually caused what we call an economical impact. And so when you perform a power quality survey, obviously, you're determining the cause and the source of the problems. The scenario is that you have a problem. It's causing economical impact. It's causing downtime. You go out, you perform the measurement, you analyze the data, and then you apply the mitigation. And so that's generally the scenario. But we also see applications where, can I add additional equipment to an existing facility? We get those kind of questions and those calls all the time. And then, of course, evaluating how power quality will impact on facilities costs. And then we see this quite often when we have the finger pointing, put you on equal footing with your utility. Very often, we use the term watching what the utility is doing by having monitoring typically on your main feeds and things of that nature. And then probably the most important in this column here, in this category, is selecting mitigation equipment. And I would underline, and I would actually add another word in there between select and mitigation. Select the correct mitigation equipment. Too many times we hear stories as far as misapplied technology, or you hear what we call these educated guesses. So going out and collecting the data allows you to select the correct mitigation, do it right the first time rather than going back and forth. And then, of course, energy survey is really pretty straightforward. You need to understand where the electricity is being consumed. That's a cliche that we use in the industry. If you're not monitoring it, you can't manage it. So I'm sure that you guys have probably heard that. Determine what the usage patterns are, identify areas where you can reduce energy. If you're involved in any type of energy management program, you're obviously going to have monitoring in place to allow you to manage that as well. So what tools do we have available when we perform a power survey? And again, a power survey may be just energy demand type monitoring, maybe power quality, maybe both. So as far as the power quality survey is, you have your handheld PQ instruments, you have permanent PQ instruments, you have more specialized tools such as oscilloscopes and fault recorders and spectrum analyzers. But the most versatile that we see in this category is usually the PQ handheld instruments. Some of today's technologies where PQ handheld instruments can also be used as sort of semi-permanent or even permanent instruments, because they have things such as communications like Ethernet or wireless communications. They have sufficient memory which can log data for long periods of time. So, out of this category here, handheld PQ instruments, or power instruments, I should say, it's probably the most versatile. Permanently installed, the mindset is usually a little bit different. You're thinking proactive rather than reactive. You're thinking what ifs. What if I have a problem? What would be the economical impact? How can I avoid that? And one of the ways that you do that is you have what we call 24/7 monitoring. Because a lot of times you see what we call precursor or incipient type events. that is often an indicator of a more sinister problem that might occur down the line. And so when you have these incipient events or you have these precursor events, that warrants taking action at that time where there's no economical impact, then allowing it to degrade to a point where you have a major power event that causes an economical impact. So that's one of the benefits of using permanently installed instruments. And then, of course, for energy surveys, it's less sophisticated. You'll have tools such as you can have handheld loggers or meters. You can have what we call panel mount or more, permanently installed type meters. You can even have existing utility meters. Your scope of work might be as straightforward as, okay, I have these existing utility meters and I'm using them manually. I go out at 12 noon, I read what the energy accumulator is, I note that down, I come back 12 noon the next day, I note the new value, and I take the delta between the two. So it might be as straightforward and simple as that. And then of course when you get into permanently installed systems, now you're getting into situations where you're using remote energy management systems. And the other thing that we should note here is that we learned this in some of the early segments, that PQ instruments often have energy capabilities, simply because PQ instruments, the resolution obviously have to be fine enough to capture those power quality events, but that resolution is more than adequate for energy type applications. So you want to keep that in mind going forward. So, and again, choosing the right tool for the job, and I sort of kind of gave it away, but the resolution of energy meters is typically measured in seconds, which makes them unsuited for power quality type applications. You can have power quality faults that might be just a few cycles in duration. So, any instrumentation whose resolution is measured in seconds is going to be inadequate for that particular application. And then, of course, when we go to PQ instruments, their resolution is typically in microseconds, which makes them suitable for recording power quality faults. But again, they can also be used in energy applications, because for energy applications, microsecond resolution is more than enough to provide accurate data. So here we're going to have our first poll here, and I'm going to pull up the poll. What do energy and power quality surveys have in common? So I'll just go and launch the first poll here. And we'll give it a few seconds for you guys to participate. Polling up. Okay, we'll give it about another 30 seconds. I see the results are coming in, so I thank you for that. And another 5-10 seconds here. And we're about a little more than halfway there. Let's give it another 10 seconds. And about 3/4. Okay, we'll end the polling. Okay, we'll share the results. And as you can see here, the results are all above. Looks like it's the majority, 67% it's all above. And let me stop sharing here, and then I'll elaborate on this. Okay. All right. So all above will actually be the right answer, because you have to think of the different approaches as safety considerations, instrument connections, transducer selection, and I will underline transducer selection because a lot of times you may have an example of not having the right transducer selection. For example, I might be using a current probe whose current range is too large for the current that I'm monitoring. Instrumentation these days, particularly the Advantage meters, are actually smart enough. They will actually tell you if the current probe is actually too large for the current that you intend to measure. So it'll tell you if you're over range or under range. And then, of course, the monitoring procedure. Of course, there's safety considerations. There's NFPA. You always have to keep that in mind. There's the ANSI standard. There's OSHA. There's local codes. There's corporate policy. Too many times, I've been with Granite since 1986, and I've seen many, many, many applications. And I've seen, let's say, people perform things that I would never dream of doing. I have actually seen people kind of reach in with their bare hands in 480 gear and things of that nature. So you want to make sure that when you're going out and you're connecting an instrument that you adhere to these standards. There's no such thing as a shortcut. Shortcuts will get you into trouble. So then there's a basic procedure. There's the planning and preparation stage. And then there's the inspection stage. And a lot of times the inspection stage will also reveal errors, especially doing new construction. So, a good set of eyes is always, it's a great tool as far as performing a survey. Of course, then there's the monitoring, actually installing the instrumentation to collect the data. Then there's the analysis, analyze the data, and analysis of data allows you to select the correct mitigation or solution. And in some cases, you may have to repeat if necessary. I like to call this the 3 whats, the 3 W's, I should say, when performing a survey. And that is the what, where, when. What's the objective? Is it a PQ objective? Is it an energy study? Obviously, if it's PQ, you're looking for those power quality events. As we learned in previous segments, SAGs is the most common voltage event. Are we looking for those type of events? Is it transients? Are we doing a harmonic study? Maybe we're doing compliance to make sure that we're complying with harmonic standards. So what is the objectives? And then, of course, for energy, it's usually is all about usage. How much I'm using, where it's consumed, when it's consumed, where to monitor. That question comes up quite a bit. Where do I monitor? Where do I actually place the instrumentation? Is it local? Is it system-wide, etc.? And then when to monitor. At specific times of the day. You want to coincide with the work cycle, for example. If I start at 8 a.m. and stop at 5 p.m., I want to monitor during the work cycle. That would be ideal. What we call the business process cycle. And this is also an important aspect as well, PQ. And people ask me all the time, how do I know if I have a PQ problem? If you characterize or catalog any time that you have a failure, if you're in the middle of your work process and the lights flicker, just note the time and date in which that occurs. Because for power quality troubleshooting, what your attempt is to draw what we call a consistent correlation. If I know that every time the lights flicker, the instrumentation that I'm using to collect the data identifies an event, and I have that consistent correlation, well, then there's a very good chance that that is the source of the problem. So that's the first place that you begin in order to mitigate the problem. So a lot of times, most of the time, you'll play detective. You'll interview operators. When did the VFD trip offline? When did the production line, when did it stop? Things of that nature. Those are all very important clues, especially if you have monitoring in place, because what you're trying to do is you're trying to establish that consistent correlation between an event occurring in the facility and a corresponding event recorded by the instrumentation. Okay. For energy, it's a lot about understanding facility, reviewing the schematic, the load types, things of that nature. Are there energy saving devices already employed? So a lot of times it's more than just simply running out to a site and putting a power monitor on a circuit and collecting data. As you can see the point here, there's a lot of preparation that you do before you even install the monitor that will help you be more efficient down the line when you're analyzing this data and making decisions as far as how to mitigate or how to save energy. So here we're going to do another poll. And this poll is, which human senses should you not use during a power survey? And I'll just, let me just bring up the question poll, and we'll launch the polling here. And we'll wait for your responses. And I appreciate your participation. And we're about a fifth of the way there. We'll give it another few seconds. And about halfway. And I'll give it another 15 seconds. Okay. All right, so we'll end this poll. And then let's share the results. Okay, so you can see that about 80, I don't know if that's meant to be humor, but yeah, 80% says taste. So we'll, so yeah, okay, so we have the results for that. Okay, all right, let's go on to the inspection stage. So use all your senses except touch and taste, obviously. And believe me, being in this business as long as I have, I actually seen people use touch. I actually seen that. I would never recommend it, but that's just something that I've seen over the years. But during the inspection, any abnormal odors, any abnormal sounds, the visual inspection is probably the most important, because you look for things like loose connections. Loose connections will show up in the measurement data as well, but if you're out there and you're doing the visual inspections, a lot of times the loose connections are a big problem. And then you also have code violations. Are you violating code? One of the most common that we see is illegal neutral to ground bonds, where you have a sub panel and you have ground and neutral bonded at the sub panel. That violates the code. So you look for things of that nature. And then for new installations, always look for wiring problems. I've been involved in many applications where, with new construction, where you've had PQ problems as a result of wiring errors. So always look for that. And ask questions. Have there been any recent changes? Any new equipment been adding? Any wiring? Any load shift? Things of that nature. So this is all part of what I call the inspection stage. And a lot of times, well, I should say, some of the times you may not even have to deploy a power monitor, because you've already identified the problem during the inspection stage. But then ultimately, when you reach the point where you have to install a monitor for PQ, where to install the monitor. If it's a localized problem, we always recommend that you install the monitor of the equipment that's being affected. So the power supply that's feeding the equipment that is being affected, that is where you want to monitor first. You start there, and then based on the results, you work your way back to the point in common coupling. Instrumentation these days, particularly the Transducer instrumentations, have algorithms that when they record events, they will actually tell you the directivity of the event, if it's upstream or downstream. So if you're going to use instruments with those type of algorithms, if I'm monitoring at a power supply that's feeding an equipment that is being affected, and the instrumentation tells me that the disturbances that are being recorded is upstream, well then now I know to work back toward the point of common coupling, back toward the service entrance, in order to track down the problem. A lot of times you may decide to monitor at the point of common coupling. That's where the customer meets the utility. That reveals a lot of information. For example, if it's energy, then obviously you're reflecting what the total building is doing because you're monitoring at the point of common coupling. If you're in a scenario where you're trying to determine if the utility is causing power quality issues, because you're monitoring at the point of common coupling, the instrumentation can identify if the disturbances are occurring upstream, which means that they're coming in from the utility, or downstream, which means they're occurring within the facility. So the point of common coupling is usually the deciding factor as far as, okay, where are these disturbances coming from? Are they coming from the utility, or are they coming from the end user? And then energy, it really depends on the survey objectives. Generally, you're monitoring the entire facility. So you're going to connect the meter at the point of common coupling, or you're going to connect the meter to each feed, because there are facilities that might have more than one feed. So obviously you're going to have monitoring at each of those feeds, and then in post-analysis, you basically aggregate all the readings together to get a total reading. This question comes up quite a bit. How should the instrument be connected? Should it be phase to neutral or phase to phase? And usually the answer to that is how are your loads distributed. If your loads are distributed phase to neutral, then the recommendation is to connect the instrument phase to phase, phase to neutral, I should say. If your loads are distributed phase to phase, then you want to connect the instrument phase to phase. That's usually the general rule of thumb as far as how to connect the instrument. Should you monitor current? Absolutely, especially if you're in a scenario where you're trying to determine where the faults are coming from, if they're upstream or downstream. Monitoring current provides that additional information. So absolutely. Okay. Instrument connection these days, particularly with the Duranus instrumentation, it has enough smarts in it where it can identify circuit types based on the number of voltage and current channels you're using and what their values are. It'll actually identify the circuit type, but there's sometimes where you may have to override that. For example, if you have a 3-phase 4-wire circuit and you want to connect the instrument up as phase to phase, because you have phase to phase loads and you want the instrument to reflect that, then the instrument may detect it initially as a Y, but you can always go in and override it as a delta. The other thing to keep in mind, and I always call this part of the sanity check before you walk away from the instrument, before you tell someone, okay, the instrument is ready to go, it's collecting valid data, is that you use some of the tools if the instrument has it available. And tools that you would use is phaser displays, you would use the scope mode display, and they would identify things such as inverted CTs. And by the way, inverted CTs or inverted current probes, whether you're using a current probe with the instrument or whether you're using a current transformer, the most common issue that we see is inverted CTs. All CTs, our current probes, have polarity markers. Some have arrows, some have X1, X2, but they all have some type of polarity marker. Sometimes you don't always observe the right polarity, and so as a result, you have an inverted CT issue. Now, it won't show up in your current amplitude reading. In fact, if the CT is on reversed or not, your current amplitude is going to be unaffected. So you're not going to go to a meter screen and see a negative sign next to an amperage reading. However, where they will occur is in your phasor display. They will occur in your watt readings, and your watt readings will be negative. If you have negative watt readings, it usually means one or two things. Either you have reverse power, I mean you're pushing power back to utility, or you have a what we call reverse polarity of the current probe. If you know that you're in a scenario when you can't possibly have reverse power, meaning you're pushing power back to the utility, then by elimination, you have what we call an inverted CT. And again, you can use tools like, in this example here, we see an example of a scope mode in which we see real-time voltage and current waveforms, and we have a phasor representation. So we can use those tools to determine if we have inverted current probes. Another very important consideration, and I mentioned this at the onset when we're kind of going through the agenda, is transducer considerations. Now, a current probe is an example of a transducer, but we use the term CT all the time. Technically, it's not a CT. If you're using, let's say if you're using a Adranus instrument and using the many current probes that are available for our instruments, technically they're current probes, they're transducers, because they take a current, they output a voltage. A CT by definition is a current transformer. So it takes a current primary, puts out a current secondary. But we use the term CT all the time. I'll probably use it until the day I'm no longer working here. I'll call a current probe a CT. But the important thing here is to make sure that your CT is appropriately sized for the load. So in other words, if I have a current probe or a CT that might be rated, let's say 1 to 3,000 amps. So the thinking is that, hey, I can use this CT to monitor 1 ampere current. For power quality, you might be able to get away with it because we're not doing any energy monitoring where we have to depend on things like the phase accuracy of the CT and things of that nature. We just want to see current so we can make the determination if a disturbance is upstream or downstream. So you can probably get away with that. For energy monitoring, it's not recommended. In fact, the rule of thumb that you would use, and what our instruments do, in particular Adranus instruments, to identify whether you're under range as far as whether the current probe is too big for the measured current, is the 10% rule. And what the 10% rule is simply, if my current probe or my CT is rated 100 amps, for example, okay? So anything less than 10 amps, the instrumentation is going to see it as under range. Now, you may be able to go to a meter screen and compare it with another meter, and the amplitude compares favorably with the other meter, but that can lead you into a false sense of security. For power quality, you'll probably be okay. For energy management, you will not, because the CT will lose its phase accuracy. The phase accuracy, once you hit 10%, begins to gradually drop off the lower you go. And phase accuracy is going to affect parameters such as VA, power factor. Those are all things that are involved in energy management. So if you want to be most accurate in that regard, you want to make sure that you're not in the under range situation. And again, instruments like the Adranus instruments, they will actually indicate when you're under range. The other thing regarding PQ is voltage and current transducers have limited bandwidth. Now, the current probes that we provide with the Adranus meters have wide bandwidth, because the idea is to pass through those events, those faults that you're trying to capture and mitigate. But you can't say that for every current probe and every current transformer that's out there. So you want to keep that in mind, particularly when you have a scenario where you might be in a medium voltage application. In a medium voltage application, you obviously can't bring the voltage and current inputs directly to the instrument. So typically you're going to monitor through existing PT and CT secondaries. And so usually those PTs and CTs are usually for metering purposes and usually don't have the bandwidth to pass through the transient events that you might be looking to record and mitigate. So that's just something to keep in mind. So now we're going to launch another poll, and the rule of thumb is the question would be rule of thumb for PQ instrument settings. So let's go ahead and launch the poll here. And number 3, right? That's number 3. And we'll launch the poll. Okay, so you guys should have the polling up here, and just go ahead and put your opinion in. And again, I thank you for participating. Yeah, so I'll just read the question again. If possible, how should you set the voltage and trigger limits for a PQ survey? So we'll just do that just in case you have trouble reading it. Okay. So we'll give it another 10 seconds. All right, we'll end the polling and we'll share the results. Okay, so we have almost half set to IEEE 519 recommendations, and match the voltage settings to the voltage tolerance of the device. And let's go ahead, I'll stop sharing the results and then I'll comment on that. And then we'll close that. So really the answer to that is if you have nameplate information of the equipment itself, then that would be ideal. There's a general rule that we use, which is the 10% rule, because most utilities will stick to the 10% rule. You know, for example, if you're having power problems in your facility, you call your utility account representative. You know, if you shout long and loud enough to get them to come out, they'll bring out instrumentation. More than likely, it might be a drainage instrument, to be honest with you. And they will connect the instrument to the point of common coupling and measure the voltage over a certain period of time. And if the voltage varies no more than 10%, then the utility is basically going to say that the voltage is within acceptable limits. And in fact, a lot of the instrumentation, including drainage instrumentation, the default settings for power quality measurement is 10%. Of course, you know, with the drainage instrumentation, you have the ability to go in and adjust it depending on the application. But in such instrumentation that do not allow you to go in and readjust the thresholds, it's usually defaulted at the 10% tolerance there. But ideally, if you can match the nameplate information on the equipment, that would be the that would be ideal to do that. If you can't, you can use the 10% rule. Okay. Here's an example of setting the instrument settings. And again, as I stated earlier, if you can match the load specification, that'll be the best scenario. A lot of times you can't find the nameplate information. So a good fallback would be using the 10% rule. You know, for example, if our nominal system voltage is 480, then we have a tolerance window between 528 and 432. And so now you've basically told the instrument what is normal. So if we have a variation that exceeds those limits, you know, then the instrument is going to record what we call the time of occurrence. It will record the min-max values, the duration, the waveform data, etc. Uh, Other considerations that you would need to think about is where you're monitoring, details of where you're monitoring. Are there mitigation devices already in place? Like surge suppressors, they can affect the monitoring results. Energy, what type of loads are present? Is it lighting, etc.? So, always consider what the environment is when you're installing the equipment itself. And then there's the sanity check. And before you walk away from the instrument, sanity check would involve, are we reading the right voltage values? Are we reading the right current? Do we have reverse polarity on any of the probes? So you use features like scope mode, the phaser display, to verify proper wiring. Uh, this is probably the most important. Make sure when you walk away from the instrument, because again, if you're doing a survey, let's say you're doing an energy survey and you want to replicate what the utility is doing, then you're probably going to leave the instrument there for at least a month. So before you walk away from that instrument, and you're not going to come back until a month later, you want to verify that all these numbers, or what I call the sanity check, that all these numbers are valid. For power quality, you're basically going to do the same thing. You want to verify the numbers are valid. You want to verify you don't have reverse polarity and things of that nature. Another common thing that we see is make sure that what's called the transducer scale factors, some people call them multipliers, some people call them scale factors. You'll hear different terms. You want to make sure that they're set correctly. If they're not, then it's going to fail the sanity check, because you're going to see current readings that not what you expect. So those are things that you want to verify. And then also, another very important point here, and probably one of the major takeaways from this slide here, is you have a scenario where you've connected the instrument, you've set it up, you've gone through the sanity checks, you initiated monitoring, and then the instrument starts filling up with event data. Now, chances are, and I've talked to many users over the years, and and usually what they do is, okay, well, it's filling up, clear the memory, start it again. It's filling up, clear the memory, start it again. Well, rather than going through that constant cycle, my recommendation is that you analyze what is filling up the memory prematurely, because you may have already found the issue that's causing the problem. The other thing too, it also indicates if you have improper instrument settings. One of the most common that you would have is the transient triggers. That's for the transient triggers is the threshold settings for subcycle events. Detection of sags and swells, that's all pretty straightforward. And just about any instrumentation that will call themselves a power quality monitor or power quality analyzer would have the ability to detect that. But a big part of power quality is subcycle events, transient events. Some instrumentation have threshold settings to allow you to set the sensitivity of such events. You can have scenarios where those sensitivities are simply set too sensitive, and then just normal switching of loads on the circuit is enough to cause the instrument to fill up with numerous events. But how do you determine that? Well, you determine that by basically doing, if it fills up prematurely, doing the analysis of the data that's been recorded in that short period of time, and then making the determination if it's a legitimate PQ event that we should be concerned with and mitigate, or is it a scenario where we just simply need to go in and readjust the threshold setting. How long when to monitor? You can you can predict when the problems will occur. It can be the time of day. Usually in those scenarios, you're going to put the instrument on, and what we've seen, you put the instrument on a start date. Let's say today is what, the 23rd, or 22nd, 23rd. So you put the instrument on, 23rd at 11:50 a.m. and you're going to leave the instrument there for a week. Typically, what we see for power quality monitors, it'll be a week for PQ. Might be a little bit longer, but the average usually turns out about a week. And sometimes you'll see data that might be relevant within that day, within a few days, but most of the time it'll be a week. If you're going to coincide it with a shift, then you would start 8 a.m., 5 p.m., or if you're going to, if it's a second shift, you might start at 4 p.m. to midnight if you want to get that specific. But generally what we find for PQ monitoring, it's usually a week. You put it on a week and collect the data. Or sometimes you'll see scenarios where you put the power monitor on and you leave it there until something happens. And that can be a day, that can be an hour, it can be a week, it can be a month. So it depends on the application. For energy, it's pretty straightforward. The recommendation here, you want to try to replicate what the utility is doing. Utility is on a 30-day billing cycle, 31-day billing cycle. That's how long you want to leave the instrument on. Too many times I've spoken to users and I said, well, I'll monitor for a week and then I'll extract it out to a month. At best you're going to get is an estimate, because you may have weeks where your energy usage might be more than other weeks. And so if you want to try to match what the utility is doing kilowatt hour for kilowatt hour, then the recommendation is one cycle, which is 31 days. So you've collected this data, whether it be power quality data, whether it be energy and demand data. If you collect this data, now you get into what I call the post-analysis. And so what are we looking for? If it's power quality data, we're looking for things that, and again, just going back some slides earlier, if during the preparation stage, if we have catalog when something failed or when something misoperated, if we catalog that and time the date, stamped it, this is the time that you're going to look to draw that consistent correlation between what you've cataloged and what the instrument has recorded. And again, if you can show that consistent correlation between what has been cataloged during the preparation stage and what the instrument has collected, then you're well on the way to determining what's causing the problem, and more importantly, selecting the correct mitigation. And then these are various different things that you might be looking for. For example, flicker. If you're in a scenario where you have light flicker, then you're posting out analyzing the data. You look to see if the flicker exceeds what the threshold is for when most people will perceive light flicker, or witness light flicker, I should say, and that is the PST, perceptibility short term. And anytime it exceeds a value of 1, most people will will witness light flicker. And as you can see here in this trend here, we clearly have a scenario in which we exceeded 1. So, and so you note the time and date in which that occurred. And if you use more advanced setups where you're going to have the instrument trigger when you exceed 1, now you have the time and date stamp when that occurs, and you draw that to some type of event, and now you have that correlation that we're looking for. And of course, with harmonics, and my experience have been with harmonics is, especially these days, is all about compliance. Am I compliant with, IEEE 519? And so, your harmonic analysis is usually evolves around that. And then, of course, if you're monitoring equipment itself, is the equipment performing as it should? A very common application that we see is what we call UPS monitoring. And UPS monitoring basically deploys two monitors, one at the input of the UPS, the other at the output of the UPS. And there's a number of things that you're looking for there. Number one, you want to make sure that the UPS is doing what it's designed for, and that's protecting the sensitive loads from variations on its input. So you're doing that. Number two, you monitor, because you're monitoring the input of the UPS, you're monitoring what the utility is doing. You know, how many disturbances and faults you're getting from the utility. And then, of course, the monitor on the output of the UPS, such as in this example here, we see that this particular UPS at this particular date and time actually failed a particular scenario where you had a swell on the output of the UPS that probably coincide with some type of event that occurred on the input, or returned to normal on the input. This is a no-no, because now your critical loads are seeing this swell. So these lines here, they represent what the tolerance is. So if you have very sensitive loads on the output of this UPS, whose tolerance is between these lines here, which is considered acceptable, then anytime you go outside these lines, outside of tolerance, now there's a potential problem for the equipment downline to either misoperate or even possibly fail. And so by having monitoring in place and the input and output, you can determine those type of things. And then, of course, compliance. You know, this is a classic that's been around for years, EN 5160, really based out of Europe, that basically shows if you're compliant of these categories here. We can clearly see that in this particular example, we were not compliant with harmonics. But that will, it can extend beyond EN 5160. What we see here commonly is compliance for THD. It's usually based on 519. So, so those are the type of monitoring that you have. And then again, we go back to that consistent correlation. Did the problem occur while monitoring? You look for events that coincide with equipment malfunctions. You know, were there any events recorded? That's a very important point to remember, because, you know, sometimes people think that, well, I've gone out, you know, with the power monitor and I put it on a circuit and it's been there a week, maybe longer, and I basically, there's no data. I haven't recorded anything. Did I waste my time? Absolutely not. When you're approaching solving power quality problems, it's all about troubleshooting. And troubleshooting is always eliminating all the factors that may be causing the problem. So now if you're going out and you connected the instrument for a week and it hasn't collected any, it hasn't recorded any events, well then, you know, the problem that might be occurring is not power related. And too many times the power gets blamed because you don't have monitoring in place. So the power gets blamed. People say, no, it's not the equipment, it must be the power. And so I hear that statement all the time. So just because you've gone out and you've monitored for a week or so and you haven't collected any faults, doesn't necessarily mean that you've wasted your time. You're just, that's part of the troubleshooting process as far as eliminating potential components that can cause the problem. Okay. And then as far as energy analysis and review, you identify areas in which you can reduce, you know, for reduction, I should say. A lot of times we see scenarios where they're verifying the energy savings, and we see scenarios where they're comparing it to a utility bill. And now we even add another bullet here. We've seen scenarios where they're verifying the accuracy of an existing meter, an existing revenue meter. We've seen many cases in which the revenue meter has been off. And with the revenue meter being off, then obviously your bill is incorrect. So there's a number of different scenarios that you would encounter here for energy data analysis and review. So what are the next steps? Next steps, do you have the in-house to apply mitigation and energy saving devices? We generally find in this scenario, no, most do not. So what do you do next? Well, if it's a PQ problem, you call your utility account representative. If the problem has been identified as the source, if it's coming in from the utility, the instrumentation tells you that your faults are upstream, which means if you're monitoring at the point in common coupling, the utility base. So you have data that you can document, you have something tangible that you can go to your utility account representative and you can say, these are the problems that are occurring. If it's internal to your facility, then generally you would, if you don't have in-house expertise, like an engineering or electrical department, and even in those cases, the engineering electrical department, when it comes to these type of scenarios, they generally don't have the expertise. And so generally they will they will contract it out to a third-party contract, a third-party source. And so now the question is how valid is that third party? Because with today's instrumentation and today's software, they make it so easy to go out and collect data and generate a professional looking report without the user having virtually no experience in this area. And so the recommendation here that if you're going to contract a third-party resource, make sure they have a proven history, check references and things of that nature. That would be my recommendation in that regard. So we're going to, I think this is our last poll here, and just do a survey here, and I'll go ahead and launch this poll. And the question to this poll, have you found our web-based, I'm sorry. Did I? Oh, never mind. I'll get the hang of this poll thing. Thank you, Ross. So the question here is, have you found our web-based power monitoring seminar series to be useful? It's actually a two-part question. And as I stated earlier, we're in the planning stage for future web trainings. What are your suggestions for future topics? Please just chat them up or email suggestions. And we'll let this go for a little bit. We'll give it another, let's see, we're about a third of the way, about half of you have voted. We'll give it another 10 seconds. Okay, another 5 seconds. And we'll end the polling. And we'll go ahead and share the results. And so the first part of the first question is, yes, I'm encouraged to hear that it was useful. I sure would like to know the one that we had voted no. Just reach out to us and tell us what we may have could have done better. We're always looking for feedback. We're always looking for improvements. It's the second question is, again, it was we're planning future web meetings. What are your suggestions for future topics? Power monitoring educational seminars. It's a very popular one. We're actually in the planning stage now, so this tells us that we're on track. And one of the considerations was educational seminars, so we're on track for that. 60% for operational training. We've also discussed that as well. So it looks like that we're hitting the right buttons or checking the right boxes in those two areas. Portable instrument training, we will sort of incorporate fixed monitoring operational training as well. So we'll cover that as well. Also software training, because with our portable instruments, the software is joined with it. That's the DramView software. So, we will basically cover all these areas here. And this is very good feedback from you. And we appreciate it. And we can go ahead and stop sharing here. We'll close this. And so that's the end of this segment. And we're going to, I see that a number of questions came in. So let's go ahead and address those questions. I want to say, what's that? Oh, you got, okay. Thank you, Ross. Thank you, Ross. I just want to say I thank you for your attendance. I look forward to seeing you in future seminars, and I want everyone to stay safe, and we'll see you in a few weeks.